On May 10, 2026, an astronomer at the Mount Lemmon Survey in Arizona flagged a faint smudge of light moving against the star field. It got a name, 2026 JH2, and a size estimate, somewhere between 15 and 35 meters across, roughly the length of a couple of school buses parked end to end. 8 days later, it passed closer to Earth than the Moon does. 4 times closer, in fact, closer than most of the satellites that keep your GPS working. 8 days. That's the entire warning window start to finish for an object that size. Discovery, confirmation, 5 separate observatories racing to nail down its orbit, public reassurance that it wouldn't hit anything. All of it happened in the time it takes to plan a long weekend. Here's the question that should follow that story, and it's not, should I be worried? It's, if that's how much warning we get for something the size of a school bus, how much warning do we get for something the size of a mountain? The honest answer is going to surprise you, and not in the direction you'd expect. It's going to split cleanly into 2 completely different stories depending on size, and understanding why it splits that way is the whole point of this episode. Let's start with the uncomfortable truth. Yes, 10 days or less is a real, current, ongoing category of asteroid warning time. It's not hypothetical. It happens routinely. 2026 JH2 wasn't a fluke. In March of the same year, an asteroid dubbed 2026 EG1, bus-sized again, 10 to 22 meters across, was spotted less than a week before it swept past Earth closer than the Moon's orbit. Go back to December 2024, and a small object burned up over Siberia with essentially zero advance notice at all. Nobody saw it coming until it was already lighting up the sky. Chelyabinsk, back in 2013, is the famous version of the same story. An object about the size of a 6-story building came in completely undetected, because it approached from the direction of the sun, where ground-based telescopes are functionally blind. Why does this keep happening? Because we've genuinely only found a sliver of the population at this size. One planetary scientist, commenting on the JH2 flyby, put a number on it. Astronomers have observed roughly 1% of near-Earth asteroids in that size class. 99 objects out of 100 in the school bus to small building range are still out there, uncatalogued, and the only way we typically find them is when they're already inbound and bright enough to spot. So if your mental model of planetary defense is, we'll definitely see it coming, that model is already wrong for a huge swath of the impactor population. The question isn't whether short warning objects exist. They do, and we're finding them on a monthly basis now. The real question, the one that actually matters, is what those objects can do. And the answer is, not much on a civilization scale. 15 to 35 meters is roughly Chelyabinsk territory. Broken windows, a shockwave, if you're extraordinarily unlucky, a direct hit on a populated area causes real local damage. It is not, under any circumstances, the kind of object that ends anything larger than a bad news cycle. Which raises the obvious follow-up. What about the ones that could end more than a news cycle? That's where the story flips entirely. Here's the flip. When you scale up from school bus to the kind of object that ended the Cretaceous, somewhere in the 10-kilometer range, the actual Chicxulub class impactor, the detection picture doesn't just improve. It's basically already finished. Objects that large are extremely bright, extremely rare, and have been getting swept up by ground-based surveys for decades. The completeness estimate for kilometer-plus near-Earth objects sits above 90%. And every one of the ones we found has a fully mapped orbit stretching out centuries into the future. There is no known object anywhere near that size on a collision course with Earth. Not a low probability one. Not a small chance in a few centuries one. None. This is worth sitting with for a second because it inverts the popular imagination almost completely. The scenario most people picture when they think asteroid apocalypse, a mountain-sized rock, 10 days notice, Bruce Willis, is precisely the scenario that's least likely to unfold that way. If a true planet killer were inbound, we would not find out 10 days before impact. We would almost certainly already know because we would have found it years or centuries ago, the same way we found every other object in that size class currently in the catalog. So, the big fear is largely handled. The small, frequent scares are real but survivable. That leaves a gap in the middle, and it's a real one worth naming honestly before we get to what's currently sitting on humanity's watch list. Every few months, a headline says some asteroid has a chance of hitting Earth. It's worth walking through what's actually on that list today because every single entry on it tells the same reassuring story from a different angle. Bennu. Currently sitting at the top of NASA's Sentry Risk List, the automated system that tracks every known object with a non-zero impact probability. Bennu's odds, roughly 1 in 2700 for a possible pass in the year 2182. That's not a typo on the year, over 150 years out. And Bennu isn't a mystery object. It's one of the best characterized asteroids in existence, because NASA's OSIRIS-RX mission physically visited it, orbited it, and scooped up a sample of its surface. We're not guessing about Bennu. We've held pieces of it. 1950. The heavyweight of the risk list, about 1.3 kilometers across, genuinely large enough to matter on a global scale if it ever did hit. Its odds, about 1 in 51,000 for the year 2880. Discovered in 1950, lost track of for decades, rediscovered in 2000, and now tracked with enough precision that 2880 is a meaningful, specific date rather than a vague someday. Apophis. The most famous scare on this list, and arguably the best illustration of the whole process working exactly as intended. In 2004, early data put Apophis at level 4 on the Torino scale, the highest alarm level any real asteroid has ever reached, out of a 10-point scale built for exactly this purpose. For a little while, this was a genuine, get more telescope time on this now moment. Then more observations came in, the uncertainty collapsed, and the impact risk evaporated completely, not reduced, eliminated. Apophis will now fly past Earth in April 2029, closer than many geostationary satellites, visible to the naked eye from parts of the world and utterly harmless. The scariest asteroid alarm in modern history ended with a really good skywatching event. 2024 Year 4. The freshest case and probably the most instructive because it shows the entire cycle happening in real time. Discovered in December 2024, its odds of hitting Earth in 2032 climbed to just over 3% within weeks, enough to trigger the first coordinated international planetary defense response to a real object. Then, as more data came in, an Earth impact was ruled out entirely. The story didn't end there, though. Attention shifted to a possible impact on the Moon instead, with odds that actually crept up over the following year, peaking around 4%. Then, in early 2026, fresh James Webb Space Telescope observations closed that door too. As of this year, 2024 YR4 will miss the Moon by about 13,000 miles. Full arc. Alarm, escalation, resolution. Inside about 14 months. 4 objects. 4 different flavors of known, tracked, and not actually a threat. That's not luck. That's what a functioning early warning system looks like when it's aimed at something big enough to see decades or centuries out. So where does the genuine uncertainty live? Right in the middle, between small enough to sneak up on us in 8 days, and big enough that we'd have already found it. That middle band is roughly 140 meters to a kilometer across. Large enough to level a city or do serious regional damage, small enough to still be hiding in large numbers. The current completeness estimate for this size class sits at around 38%. Put that gap in human terms and it stops being an abstraction. In 1908, an object somewhere in that size range, estimates vary but likely in the tens of meters, detonated over the Tunguska River in Siberia and flattened roughly 2,000 square kilometers of forest, with an energy release on the order of 1,000 Hiroshima bombs. No one saw it coming because in 1908 nothing was looking. It hit one of the most sparsely populated places on Earth. If the same object had arrived a few hours later, rotation would have put a mid-sized city under it instead of taiga. Fewer than 4 objects in 10 in a size range capable of genuine regional catastrophe are currently catalogued. The rest are out there, unfound, on orbits nobody has mapped yet. This is the actual gap. Not will a planet killer sneak up on us. It won't realistically. It's could a city killer turn up with a few years' notice instead of a few decades? And right now the honest answer is, yes it could. The fix is already funded and already under construction. NASA's NEO Surveyor, an infrared space telescope purpose-built to hunt this exact size class, is targeting a launch no earlier than September 2027, parking itself at a gravitationally stable point beyond Earth's orbit where it can watch for asteroids without the sun's glare blinding it, the same blind spot that let Chelyabinsk through. Within about 5 years of operation, it's expected to roughly double our knowledge of this population. Within a decade, It's targeting the 90% completeness threshold that we've already hit for the bigger objects. Ground-based efforts are closing the gap too. Newer wide-field surveys are projected to add tens of thousands of new cataloged objects in this size range over the next several years, on top of everything space-based instruments turn up. None of this closes the gap tomorrow. But it puts a specific, funded, under-construction date on when it closes, which is a very different situation from we have no plan. Detection alone doesn't stop an impact. It buys time, and time is the entire game because moving an asteroid is not a matter of brute force, it's a matter of patience. The physics is almost boringly simple. Nudge an object's velocity by even a tiny amount early enough, and that tiny nudge compounds over years into a miss instead of a hit. You don't need to blow anything up. You need to change its speed by a whisper, decades before arrival, and let orbital mechanics do the rest. We know this works because it's already been tested. In 2022, NASA's DART mission deliberately slammed a spacecraft into Dimorphos, a small moon orbiting a larger asteroid, and measurably shortened its orbital period. Proof in the real world, not a simulation, that a kinetic impactor can meaningfully alter a small body's trajectory. Follow-up missions are underway to characterize exactly how much debris that impact kicked up and how the physics scales to larger targets. Other concepts: a gravity tractor spacecraft that hovers nearby and tugs an asteroid off course using nothing but its own gravity, applied patiently over years, exists specifically for the scenario where you have a long lead time and want a gentler, more controllable nudge than a direct hit provides. Here's the catch, and it's the same catch every time. All of these methods need years to decades of lead time to work. A gravity tractor is useless with 10 days notice. A kinetic impactor needs enough runway for a small velocity change to add up to a meaningful position change by the time the object would have arrived. Warning time isn't just about knowing, it's the raw material that every deflection option is built out of. No warning time, no options. Decades of warning time, and even a fairly modest, well-tested nudge is enough. So, back to the two scenarios from the cold open. 10 days surprise versus decades of preparation. Which one is real? Both are, and now you know exactly where the line falls. The 10-day scenario is real, ongoing, and happening roughly monthly, for objects that, at worst, break windows and rattle nerves. The decades of warning scenario is also real, and it's the one that applies to everything large enough to actually threaten a city, a region, or civilization itself, because those objects are either already found or on a funded, dated path to being found within the next decade. The gap in the middle, regional catastrophe scale objects we haven't found yet, is the one place where the two stories could still blur together. It's real, it's honestly still open, and it's the one part of this picture that isn't finished yet. But it's also the one part actively being closed, on a specific timeline by a specific mission right now. 13 billion years of cosmic history built the raw material, dead first stars, a solar system that didn't stay where it started, a debris field we're only now learning to count. Somewhere in that debris field is the next object that will make headlines. The honest, current answer to how much warning will we get is, for the objects big enough to matter, probably a lot. For the ones that don't matter as much, we'll keep finding out with about a week to spare, and that turns out to be fine until the next time.